All right, I just want to make sure we're all on the same page with what's going on here with this uh, function and what we call modeling with the quadratic function. First of all, kind of just some background here. This general formula here is developed through some calculus using what we call differential equations, which use derivatives and it is ultimately about a bunch of slopes. Differential equations, a college course that you take Calc 1, Calc 2, Calc 3, and then probably differential equations after that. But this is the generic format, and many of you that are in physics might see something like this. H of t, sometimes they say S of t for position or height in this case, but we're going to rewrite it as negative 1/2 g t squared plus v sub naught t plus h sub naught. Okay, and like I said, you might see it at some stage h replaced with s or s replaced with h, doesn't really matter. But this is the general format, and this is what I was talking about with the differential equation that we get from calculus. Now, we do a little bit of work with this to get it into a format that we're used to. Basically, what this g means is that's the acceleration due to gravity. In regards to a calculus class, the derivative of a position is speed, and the derivative of speed is acceleration. So acceleration is very in tune and wrapped in with position here. So that g, and in a physics class, you know, gravitation, acceleration due to gravity is approximately 9.8 meters per second or per second squared. And in regards to feet, that's about 32 feet per second squared. Okay. So when we take negative 1/2 of that, we get negative 4.9 for that term, and then we'll go t squared plus v sub naught t plus h sub naught. So there is one position function, and that's in regards to meters. Okay, so that's going to tell us our height in meters. The one we're dealing with here, and I think we see for the most part during this course in advanced math, is they're going to do things in feet. So we take 32 and multiply by negative 1/2, we get negative 16 t squared plus v sub naught t plus h sub naught. Okay, and that will then provide us solutions in feet in that unit. And this is really what we've got to pay attention to and understand. Now you see up here that they don't have this h sub naught. H sub naught is simply an initial height. So what that means is maybe instead of, in this problem here, when we write this equation down, go ahead and write it down as h of t negative 16 t squared. Okay, that negative 16 is constant for every single one of these problems we do when we have a projectile. Plus then v sub naught. So that's the initial velocity. That's the propellant that is forcing this, in this case, this bullet to be shot. And we're seeing that's 800. So we put 800 and then t. If I were to do this problem, maybe I'm standing on a building. Okay, maybe I'm standing on the second floor of a building. Maybe I put plus 20 feet for to get that initial height off the ground. Okay, so if it's 0, like it is in this place, we can interpret that we're doing this from the ground. And if I want to do it from an elevated position, I just add whatever that height is. Okay, so this is the problem we're dealing with. Now, what I want you guys to understand, I want to go back to this GeoGebra applet here to kind of explain what is going on and what this function is relating to. Okay, in general, when we deal with projectiles. Okay, so let's say this is, let's just reset this back to, let's do it this way. When we deal with projectiles, most people kind of visualize like throwing an object or shooting an object, and the path of that bullet or ball that they've kicked or ball that they've thrown, or if you're a big baseball fan, a lot of times they'll tell you that if somebody hits a home run, this is how many feet it went. Well, they're using this type of projection to estimate those distances. Okay, and this is how it's done. We have an initial velocity up here, and that's just going to say, this is how fast we're throwing the ball, or maybe this is how fast this bullet is being shot, or whatever. So I'm just going to, and there's arbitrary values, right, and they're in meters. So I'm going to say that 33.5 meters per second is my initial velocity. Now my launch angle, we can change these. If you watch baseball, they talk about how when a hitter hits a home run, they can calculate the launch angle of that ball at the instant that the ball was hit. So it's pretty interesting. But I'm going to change that launch angle. Let's just go 40 degrees here. Okay, and I can fire that object. Okay, and we see that the object is taking this parabolic course. Okay, so I'm just taking that parabolic course. Let's speed this animation up, and we'll just reset it and fire again. But we take that course. Okay, that's maybe a little bit too fast. And what this does is this tells me, this dotted line is the path of the course, or the object, and it just tells me what we call the horizontal and vertical displacement. Basically, this ordered pair right here is an x distance away from where it started, where it was shot from, and this y distance is how far vertically it is away from where it started. Okay, so this is kind of a visual. And if maybe you're a tank down here and you shoot a ballistic, and this is the path that ballistic takes in that two-dimensional space. Okay, that is not what we're dealing with in this class right now. Okay, you will deal with this in a calculus in a calculus course, or most specifically probably in your physics course. What we are doing is we're saying, okay, if this is the situation where we're now going to, instead of having a 40-degree launch angle, we're going to have a 90-degree launch angle. So we're going to shoot this thing straight up in the air. Okay. What's going to happen, just mess with my velocity there a little bit. What's going to happen is I'm going to shoot this, just looking at the stuff over here on the left-hand side. If I fire, and we see all that ball, that projectile went up, kind of reached its maximum, and then came straight down. Okay, and that's the idea. That's what you would visually see if you threw something straight up or shot something straight up. You're not going to see a horizontal distance displayed. You will see a vertical distance, but you're not going to see this thing move away from where it was shot. It's going to come back down. You think about shooting a bullet straight up in the air. We eliminate all other like physics, like wind and friction, all that kind of stuff. If I shoot a bullet straight up in the air, that bullet should come and return right back down to where it came from. We see over here it's a little bit of a different picture. Okay, so I'm going to zoom in and just refire this. So reset, fire. Okay, so what's going on here is we see, this is going up and it's coming back down, but over here now we're actually seeing a parabola, and that's because this side here, or this axis, is now a time axis. Okay, and this is the height axis. So what we're seeing here in this case is an h. Give me a second. Okay, let me reset and fire again. Okay, so what's going on over here is that we're dealing with that. Sorry, we'll get it eventually. Fire. Stop. Okay. So what we're seeing over here is that this axis is our time axis, and this axis here, the y-axis, is our h of t, which is our height at some particular time. So every little one of these ordered pairs that you're seeing showing up as a red dot here is some time, comma, some height at that time. Okay? So this is representing that these are ordered pairs that are coming from this expression where we had -16 t squared plus some initial velocity times t. And if you see over here, this would be negative 16 t squared, initial velocity 17.5 t. That would be that function. But what we're seeing here is the idea that every time I throw an object straight up in the air and it comes straight back down, its height measured against time shows us this parabola. Okay? And that parabola is then modeled by that function, negative 16 t squared v sub naught t plus h sub naught. Okay? And we see over here then that all of these points would be ordered pairs. And you see that I need to stop it. But what's going on here is that, for instance, at this interval, not interval, but position, let's fire it again. Let's stop it right there. It looks like at this stage here, obviously, at that point right there, the height is 0. So we got the point 0, comma 0. Time is 0, height is 0. Over here, it looks like we have a time of about 3.6 and a height back down to 0. Okay. Here in the middle, it looks like we have about a 1.8 as our time and a height of maybe 15.8 or something like that. Okay. So again, all these points are t, comma, the height at that time. What we're seeing a lot of our questions is they're going to ask, what was the maximum height that this object reached? Well, the maximum height is this 15.8 here. It's the height at that time in which we were at the vertex. They might ask questions like, what was the time in which it reached its maximum? Well, that's 1.8. That's the t value. And they're going to ask you, when did this thing return back to ground? Well, when we see the word ground, that's a key phrase for saying your y value is 0. So they're asking, when did this thing hit the ground? Our y value is 0. The time that it took then to hit the ground was 3.6. Okay, so this object was in the air. If we come back over here, we go back in it goes up, and then it comes back down. That's a terrible picture, but the idea is that thing was in the air, going straight up and then straight back down for 3.6 seconds. Okay, so let's go back to this particular problem and kind of work out the nuts and bolts of what the question was asking. All right, so we create from this information, we create the quadratic equation that h of t is equal to negative 16 t squared plus 800 t. Okay, and that's the description here. Now the rest of the question asked us a couple things. Asked us, I think, 4 things, and we're going to walk through and come up with those 4 things pretty quickly here. And ultimately, just being able to factor is going to allow you to come up with these values. Okay, so we're now looking to answer these 4 questions. When does the bullet fall back to the ground? When does it reach a height of 6,400 feet? When does it reach a height of 2 miles? And how high is the highest point the bullet reaches? So first thing I'm going to do is we're going to take this picture, and I'm going to think about what it means to come back down to ground level. Okay, so we've got our height here, and we've got our time. Okay, so here's our t-axis again. Here's our h of t, our height. And we know this thing's going to go up, and it's going to come back down. Okay, hopefully it looks parabolic when we draw it. But this is going to be time equals 0, and this is the time that we're looking for over here. We're looking for this time. Okay, but what's nice about that is that we know at that time, whatever it may be, the h of t is 0. And the same thing over here, this h of t is 0. So what we should be able to do then is take this original equation that we came up with and say, okay, if h of t is 0, I get negative 16t squared plus 800t. I should be able to now solve this for t. And when I solve it for t, it's going to give me that value there, hopefully, t equals 0, and this value here that we're looking for. Now, because we can factor, so I'll take out a t, gives me negative 16t plus 800. I could have probably taken something out of the 16 and the 800, but don't really care to do that. I get negative 16t plus 800 is equal to 0. I can solve that for t, and I believe I'm going to get t to be 50. Okay, so I come down here and I say, okay, t is 50, and that tells me then when the ball came back down to the ground. You see, you get 2 solutions. When was the ball back to ground level? Well, it was at ground level at the initial time. Before we did anything, this thing was sitting on the ground. 50 seconds elapse, and it has traced out its the straight up and the straight down pathway. But it took 50 seconds to do that, to go from where it started, to go all the way up to its maximum height, and then come back down to the ground. Now it says, when does it reach a height of 6,400 feet? Okay, well, it's the same question, but now instead of being worried about when this thing hits a zero height, we're interested in when does it hit 6,400 feet. Okay, well, now it's a quadratic equation where we get 0 is equal to negative 16t squared plus 800t minus 6,400. Okay, now you might be a person that likes to make that positive, that negative, and that positive. I would. And now we're going to try to factor that. Okay, I'm going to just do something real quick here, because just to save some time in factoring, we're going to use my calculator. 16t squared minus 800t plus 6,400. All right, so that thing doesn't really factor really nicely, so here's what we're going to do. If it doesn't factor real nice, we can always say x is equal to, or t, I guess in this case, t is equal to the opposite of b. So b was negative 800, so we're going to say 800 plus or minus 800 squared minus 4a being 16, c being 6,400, all over 2a being, in this case, 32. So give me a moment, and I'll calculate that for us. Okay, so when we put this into our calculator, or however you're going to solve this, we first get t, and when I do the 800 plus, I should get 1280 over 32, which evaluates to 40. Okay, so at a time of 40, this thing has reached a height, so that point right there, time of 40, reaches a height of 6,400. Okay, so we're seeing right there that might be 6,400 on the y-axis. Now just real quick, so I've got it on my calculator, we'll do the minus one. Should be symmetric. We'll find that out when we do these parabolas. A lot of symmetry. I get, if I do 800 minus the discriminant, I get 320. 320 divided by 32 then is 10, so t is 10. So now we got 10 there, comma, 6,400. So at 10 seconds it reaches 6,400 feet in the air. It goes through, keeps going through. After 40 seconds, it's going back down through 6,400 again. Okay, so those are the two values we're looking there. T is 40 and 10. It says, when does it reach a height of 2 miles? Okay, let's actually, it says how high is the bullet point, or what is the highest point the bullet reaches? Let's do part D first. Okay, so the highest point, in this case, and maybe early on these problems are maybe a little bit easier doing it this way, is that we know parabolas are symmetric. Okay, there's a line of symmetry that goes through the vertex, which is the highest point here. Well, if I know my x-intercepts are at 0 and 50, halfway in between 25, okay, I should have my maximum. Okay, so I should have my maximum here at a time of 25. Well, if that's t, shouldn't I be able to say h of 25 is equal to negative 16 of 25 squared plus 800 times 25? And that will tell me h of 25 is equal to, just real quick, negative 16 times 25 squared plus 800 times 25 gives me 10,000. Okay. Which may, that number kind of makes sense with, 10,000 isn't that much bigger than 6,400. Okay. But that's the highest point that we're getting for this projectile. Okay, that's the highest it would get. So going back to this image here, if we would fire it and stop it at its maximum, so this point here we're saying would be 10,000. Same thing over here. Now disregard this axis, these numbers on it, but we're saying that height right there would be 10,000. And you start to see the symmetry that we talked about in regards to this problem. If that's the axis of symmetry for the parabola, then I go 15 units to the right, I get the 6,400. I go 15 units to the left, which would have been 25 minus 15 is 10. I get back to 6,400 and so forth. Okay. Now the question is, part C, when does it reach 2 miles? Well, 2 miles would be 5,280 times 2, which is greater than 10,000. Okay. So does this parabola ever reach this black line up here? It never reaches 2 miles, so it never gets there. Now, algebraically, what that would mean, okay, how would we solve that algebraically? We would say, 5,280 times 2 is going to provide you with 10,560, and now is equal to our position. So if you were to solve that, so move this over or move these over, so you get 16t squared minus 800t plus 10,560 is equal to 0. If you solve this for t using your quadratic formula, you're going to get underneath your discriminant. Okay, think about this. Our discriminant, 800 now, it's opposite, or sorry, it's b squared, so 800 squared. I don't care if it's negative, because I'm going to square it, so either negative 800 or positive 800. But now it's minus 4 times 16 times c. And c is 10,560. So if I do that real quick, I'm going to go 800 squared minus then 4 times 16 times 10,560. It gives my discriminant now to be negative 35840. I don't care what the numbers out front were and what the denominator was in this case for my quadratic, because that's negative square root, and we know we can't do that. We get imaginary numbers, and that algebra then tells me, because I shows up, okay, hopefully we all realize that. If I go ahead and evaluate this, take the 35840 number, take the square root of that, it gives me approximately 189.3i. Okay, if I were to evaluate it out to the nearest tenth, but we can't graph that, which ultimately tells me that there is no intersection between that line and that parabola. Okay, and that's the idea, the concept that we talked about in class, where we need to be able to take the algebra that we're doing and make a connection with a picture, or make a connection with a physical application. And this algebra, when I develop I's in regards to this type of problem, tells me I don't have intersection of, in this case, 2 miles. Okay. We'll talk about this again in class, but I think that's nice to have, that explanation. You can stop it, pause it, rewind it, re-listen to it, that kind of stuff. That's all I've got.